Good afternoon, esteemed colleagues, industry professionals, and aviation enthusiasts. Welcome to the second sessions of Singapore Polytechnic's Future Horizons webinar series 2025. Okay, I'm delighted to see so many of you joining us today for what promised to be an enlightening 2-hour explorations into the cutting-edge world of sustainable aircraft systems. Today's sessions titled Recent Developments in Sustainable Aircraft Electricals and Electronic Systems couldn't be more timely as we stand at the crossroad of technological innovations and environmental responsibility. The aviation industry is undergoing a remarkable transformation. In the next 120 minutes, we will embark on a journey through the latest advancement in both manned and unmanned aircraft systems, for revolutionary power generations techniques to groundbreaking energy storage solutions. We will examine how these innovations are reshaping the future of flights. We are privileged to have two speakers with us today, Mr. Shankar Maniam and Dr. Tan Hui Xiang, both senior lecturers from Singapore Polytechnic, will be sharing their expertise and insights. They will guide us through the intricate world of sustainable materials, operations, and processes that are propelling the aviation industry towards a greener horizons. As we delve into this topic, I will encourage you to ponder how might this advancement impact your work? What role can each of us play in driving sustainability in aviations? And perhaps most interestingly, how might these innovations in aircraft systems influence other industries? So fasten your seatbelts and prepare for takeoff. We are about to embark on a journey into the future of sustainable aviations. Let's soar into the new realms of possibility together. Without further ado, let's begin our explorations of the electrifying world of sustainable aircraft systems. Mr. Shankar.
Okay, thank you, Mr. Tan Teo Kui. Welcome to the Main Aircraft Electrical Electronic Systems under the big topic of recent developments in sustainable aircraft and electrical electronic systems. I'm Shankar Maniam. I'm with the School of Tripoli and I teach aircraft electrical systems mainly under the Diploma in Aerospace Electronics course. Let's move on with this topic. So first, let us start with the main objective on sustainable. So the topic is about sustainability, and sustainability is on everyone's lips now these days in every area, from hobbyists to social media networks and all the way up to even aerospace. And under the aerospace uh, discipline itself, we are specifically going to look in the electrical and electronic systems arena. But before that, let us just look at the word sustainability itself and remind ourselves, like, what is it and why are we talking about sustainability? So to borrow the definition of sustainability from United Nations, it's about the meeting the needs of the present without compromising the ability of future generations to meet their own needs. So we are trying to not compromise anything in the present, but at the same time, making sure that it does not prevent the future generations from meeting their own needs. So, Sustainable Development Goals under the United Nations is about improving the lives and at the same time mitigating the hazardous man made effects on climate change. So, these are like the foundation stones that's been laid out. And now we are going to look into the specific area on how aircraft systems are contributing towards this sustainability goal. So, next question is, why then are we talking about sustainable aircraft design? I mean, what are the motivations behind this? So first we look at environmental impact. We want to reduce the carbon footprint of aviation to combat climate change. In fact, in 2023, IEA estimated aviation to account for about 2.5% of global energy-related CO2 emissions. So that's like having grown between 2019, which is like the pre-pandemic period, compared to the other modes of transport like rails, roads, and shipping. So we have, like in aerospace sector, quite a large jump in the carbon emissions. So that's one of the reasons why we are looking at sustainable aircraft design. Another one is the regulatory pressures. Uh, Now sustainability is on everybody's mind, and in 2022, ICAO member states adopted a long-term aspirational goal. In short, it's called the LTAG, to achieve net zero carbon emissions with an ambitious target of by 2050. Now we're at 2025, so we got like 25 years to meet this long-term aspirational goal to achieve net zero carbon emissions by our aviation community. So we have environmental impact and regulatory pressure. Next, economic benefits. So sustainable aircraft can actually lead to cost savings in the long run. For example, using renewable energy sources and more efficient technologies can actually reduce fuel consumption and maintenance costs. So economic benefits is another driver to lead us in the direction of sustainable aircraft design. Next will be consumer demand. So there was actually a study done to see what do consumers say about sustainable aircraft design, because most of the time when we talk about implementing sustainable aircraft design, the cost is often going to be transferred to the end user, which are the customers. I mean, that pretty much applies to any other industries. So in the context of aircraft design, what are the customers saying? I mean, how well is it going to be received if we say that the cost to the customers, the end users of aviation, is going to increase? So the study showed that in 2022, there was a study, and the study showed that the consumers are actually willing to pay up to 12.7% more for flights that are prioritizing sustainability. So some of the key attributes in terms of this prioritizing sustainability is in the area of reducing carbon emissions and using renewable energy sources, as well as minimizing waste. So that itself is a positive sign for the airlines and aircraft manufacturers to adopt greener practices, because it's going to attract environmentally conscious customers, and it's believed that this base is going to increase. So that will probably also enhance the reputation of these customers, of these brands to their customers. And then it's also leading towards the corporate social responsibility, because aerospace companies with customers are like more willing to pay a slightly higher premium for sustainable aircraft, and therefore aerospace companies are motivated now to make it into their corporate social responsibility and recognize that it's important for them to part of the overall sustainable design, add in these initiatives to get a better footing among their customers. And lastly, on the why sustainable aircraft design topic, we look at the technological advancements. So innovations over the years in the area of propulsion systems, energy storage, and materials are actually making it feasible to design more sustainable aircraft. So with these innovations in technology, it's making it more feasible to have to implement these designs in the aircraft such that the aircraft itself becomes sustainable. So these advancements are actually pushing the boundaries of what was previously thought not possible to now like becoming more and more possible. And that is the area what we are focusing on in this topic. So sustainable aircraft electrical and electronic systems, largely among these main drivers and motivation for sustainable aircraft, is anchored on technological advancements, and that's where today's topic is going to cover. So my area will be talking on the manned aircraft, and later on my colleague Dr. Tan Huisiang will be talking about the unmanned aircraft from this perspective in terms of the technological advancements. So now let's begin by looking at how sustainable electrical and electronic systems contribute. So technological advancements in electrical and electronic systems play a pivotal role towards the success of sustainable aircraft systems in the following areas. So first, it will have improvement in fuel efficiency. Next, we will have reduced reliance on fossil fuels, lowered emissions, simplified maintenance, and all these will lead towards a sustainable aircraft design. So all these 4 points are the end results that we will benefit from sustainable electrical and electronic systems. So how will these sustainable electrical and electronic systems contribute towards the sustainable aircraft design? So still on the topic on how these sustainable electrical and electronic systems contribute, I have summarized it, or rather classified it into 5 main areas that we will look at in this presentation session. So first, we will look at more electric aircraft. Secondly, we will look at advanced energy storage technologies. Third, we will look at power management and distribution. Fourth, we will look at the integrated modular avionics. And lastly, we will look at lightweight materials, components, and manufacturing processes. So these 5 areas under the electrical electronic systems are what we are going to look at, and how these advancements in these areas will contribute towards a sustainable electrical electronic systems in the aircraft design. So let's start off with the first one. More electric aircraft. So more electric aircraft is actually the replacement of traditional hydraulic and pneumatic systems with electrical ones. So traditional aircraft, they are mainly using hydraulic pneumatic systems, which are heavy and require a lot of mechanical parts. And the more electric aircraft tries to replace them with electrical parts, which are far lighter and requires lesser parts. So recent developments in powerful and efficient electric motors, generators, power electronics are actually accelerating the progress in these advances. And how it's accelerating is in the form of an all-electric or hybrid electric propulsion systems. So the more electric aircraft is gearing towards, or rather focusing on, the propulsion systems of aircraft, and it's making it into a less fuel-driven propulsion system and more towards the electric propulsion system. So what's the main difference between all-electric propulsion system and the hybrid electric propulsion system? A fully electric propulsion system will rely solely on electric motors powered by batteries or other electrical sources, where we eliminate the need for fuel. So it completely does not require fuel, and it will be relying solely on electric systems. Hybrid electric propulsion system, on the other hand, combines a conventional internal combustion engine, some kind of a fuel-driven engine, but with an electric motor. So it's a hybrid system where it uses the conventional method of an engine, and as a complementing that, it will have an electric system that will work together, and that will allow for improved fuel efficiency and reduced emissions. Of course, not as much as a fully electric propulsion system, but a fraction of it. So if we are able to make it into fully electric propulsion system, then why are we even talking about a hybrid electric propulsion system? There are some reasons for this. One is the energy capacity. So current battery technology has lower energy capacity compared to fuels. So this will limit the range and endurance of a fully electric aircraft. So if you have a fully electric aircraft and we need to use it for a long range flight, then it will not be able to sustain that range compared to a hybrid propulsion system, because the fuel-driven engines have much more higher range and the endurance to cover a longer range. So that is one of the reasons why hybrid systems are still being deployed compared to a fully electric propulsion system. Next is the infrastructure limitations. Unlike the well-established fuel infrastructure, charging and electric maintenance infrastructure are all still developing. So this will also be a hindrance at this point in time, because if we have everything fully electric, then the existing infrastructure may not be able to support the fully electric aircraft. Next is the weight. Batteries impact the payload and efficiency of fully electric aircraft. So if we want to have a, let's say, long range aircraft that is fully electric propulsion system, then the amount of batteries to sustain that same amount of a longer range compared to a fuel based propulsion system will be much higher, and that will impact the payload and efficiency of the aircraft itself. So weight becomes an issue. So in short, hybrid electric propulsion systems serve at this point in time as a transitional technology where it allows the gradual adoption of electric propulsion while still leveraging existing combustion technology. So we may not be able to fully get the full benefits of a fully electric propulsion system, but then having a transitional technology will still be able to allow us to reap some benefits, not full, but parts of it, and geared towards the full, getting the full benefits out of it. So, as a summary, the conventional aircraft propulsion systems over here, it's running on fuel, and then it's going to be powering the engine, sorry, and then the engine will drive the propeller. In a fully electric aircraft propulsion system, we will have battery, and the battery will just drive a motor, and the motor drives a propeller. That's a fully electric propulsion system. For the hybrid electric propulsion system, we will have both. We will have the fuel supplying the engine will drive the propeller. At the same time, the battery concurrently will supply to the motor, and the motor will drive the propeller. So we have both the fuel and engine system as well as the battery and motor system driving the propellers to generate thrust for the aircraft. Let me get the laser pointer. Okay. So that is the more electric aircraft. Now let's look at some examples. So we have the fully electric propulsion aircraft. First, we have the Pipistrel Alpha Electro. It's actually a two-seat electric trainer aircraft. It was designed in 2015, about 10 years ago, by a Slovenian manufacturer. And it was meant for pilot training and short-range flights. And it is, in fact, one of the first fully electric aircraft to have airworthiness certification in the US, Canada, Australia, and some of the European countries. So this is one very good example of a manned aircraft, and it's got more than one person in the aircraft, which is not just a pilot, but a two-seat electrical trainer aircraft, and is fully electric. Then we have another aircraft, which is the Aviation Alice. This is a fully electric commuter aircraft. It's designed by Aviation Aircraft in Israel. It is intended for regional flights and has been undergoing testing and development, with first flight that happened in September 2022, which is about 3 years ago. So I have a video here, but we will maybe watch it at the end of the session. Otherwise, it's a short YouTube link. You can watch it on your own subsequently. There are many more aircraft. For example, Boeing still retains a stake in one of its advanced air mobility sector, as well as Embraer and Textron. They are all working on eVTOL, that means electronic vertical takeoff and landing aircraft, and all geared towards making it a fully electric propulsion aircraft. So work on this area has not just started, but there are a few success stories in terms of fully electric propulsion aircraft. But as I mentioned in the previous slides, there's still a limitation in terms of its range and endurance. Moving on to the hybrid electric propulsion aircraft. So some examples will be the Airbus E-Fan X. This was one of the early projects that was handled by Airbus, Rolls-Royce, and Siemens together, where one of the four jet engines were replaced with an electric motor. So the aircraft had four jet engines, but one of it was replaced with an electric motor. So if you were to recall the earlier block diagram on the more electric aircraft, but then the hybrid electric version, we have a combination of both the fuel-driven engine as well as the battery-operated motor, both acting on the propellers to provide thrust. So this is one example of it. Three engines, jet engines, and one electric motor, all working on the propellers to provide generate thrust for the aircraft. Unfortunately, the project was discontinued in 2020, partly because of the pandemic, and after that, not much work has been done on it. Nevertheless, it was a significant step towards the hybrid electric aviation. So it was like a stepping stone, and a lot of learning was uh, happened from this project. And subsequently, we have a more successful version, which is the Ampere Electric Eel, a hybrid electric aircraft that was developed by Ampere, and it was based on a Cessna 337 Skymaster. The Cessna 337 Skymaster is an interesting aircraft because by itself, it is actually a push-pull aircraft where the two engines of the aircraft are not in a conventional format where both propellers are at the side, where here in the Cessna 337 Skymaster, we have one propeller in the front and one propeller at the back. So typically, the propeller in front will pull the aircraft forward to provide thrust. And over here, the rear propeller, instead of pulling, is actually pushing the aircraft forward. So that's why it's called a push-pull configuration. And in this project, this is the Cessna aircraft itself. But for the Ampere Electric Eel, the project was where the forward piston engine of the Cessna 337 was replaced with an electric motor that was powered by a battery. So one aircraft propeller, which is at the back, and that is like engine driven. The other one is battery driven. So it's a hybrid propulsion system. And it had a successful flight on 10 December 2023, just 2 years back. And it demonstrated a 12-hour endurance flight for more than 2 hours. And it endured a 12 hours endurance flight with more than 2 hours of fuel and battery reserve. So that was a pretty successful demonstration. And in fact, the EEL demonstrator aircraft has high power electronics, inverters, and motors. All these are the electrical electronic systems that led towards a hybrid propulsion system, hybrid electric propulsion system in the aircraft, and it achieved 50 to 70% kind of reduction in fuel consumption. So it was a very successful aircraft, still in operation, and in fact, work on it has been happening, and it's on its way to getting certified. And a fun fact here is that the 12-hour endurance flight covered a path of about 2,212 kilometers. And in our context in Singapore, it's like equivalent to flying from Singapore to Laos, about 2,063 kilometers. So that's a decent range that was covered by this hybrid electric propulsion aircraft. Now let's move on to the advanced energy storage technologies. Solid state batteries. So solid state batteries are very new in the sense that the solid electrolytes are used in the battery instead of liquid ones. So the electrolytes in traditional batteries, like the lithium-ion batteries, they are going to be they are actually in liquid form. But here, solid electrolytes are used in the batteries. And what does it offer? It offers higher energy density and improved safety and longer lifespan. So unlike lithium-ion batteries, where these solid-state batteries reduce risk of leakage and thermal runaway. So reduction of risk and thermal runaway is actually very suitable for manned aircraft. In the manned aircraft, the batteries are usually in compartments where it's hardly visible, and any form of a leakage will lead to corrosion of the aircraft's compartment body, and that will lead to like maintenance and other may lead to even safety related issues, as well as having a thermal runaway in the battery will lead to like safety risk. And here we are having a solid state electrolyte instead of liquid, and that is very suitable for manned aircraft because it will reduce these risks that I just mentioned. So solid state batteries, however, faces significant challenges. What are the challenges? One is to manufacture it at scale. That's going to be a very complex operation because at this point in time, the technology is still slightly past its infant stage. So to bring it up into a production and manufacturing it at a large scale is pretty complex, and that leads to making it more expensive than conventional batteries. And also dendrites. Dendrites are like needle-like structures that grow inside the battery. It's quite prevalent in these solid state batteries, and that will have a risk of causing short circuits. And that these are like the present technical hurdles. So we have both the economic cost-related hurdle as well as the technical hurdles that need to be overcome before solid-state electrolyte batteries becomes mainstream, at least for aerospace application. Another advanced energy storage technology will be the lithium sulfur batteries, and these are high energy density batteries, and it's got a lower relative weight. So 500 watt hour per kilogram compared to lithium ion battery for the same energy density, it will be about 220 watt hour per kilogram. So that is making these lithium sulfur batteries more attractive, where weight is a critical factor. And when it comes to aerospace applications, anything to do with weight is a sensitive topic. We always want to have things lighter in the aircraft, and therefore this has actually gained much attention in the aerospace applications area. However, it doesn't come with it's not like it comes with no challenges. There are a lot of challenges that comes with it. Some of it are to overcome the improvement to the cycle life. So the charging, discharging will actually diminish the cycle life. So that's one issue. And the other one is the degradation of sulfur cathode. So these batteries are using lithium and sulfur. So the degradation of sulfur cathode is a problem in this current version of the technology, and that needs to be overcome. So if we were to look at these pictures here, NASA has shown a lot of interest in the solid state batteries, and a company called a company called Lytton is very much involved in solid state batteries, and the reasons for them to be very interested in this area is because of the very attractive features of high energy density and relatively low weight. So this is something that is driving this technology in the aerospace area. So if you see these small little prints here, it shows that these lithium batteries has resulted in about 50% weight reduction compared to other forms of lithium ion batteries. And some other batteries, in fact, the performance of lithium sulfur batteries goes up to like 75% weight reduction. So that is something that is making these lithium sulfur batteries very attractive for applications in manned aircraft. Let's move on to the next part. Still on energy storage technologies, this is the hybrid energy storage system. So in short, it's called a HESS. This is a unique hybrid system where it combines batteries with supercapacitors. And the purpose of doing that is to achieve better performance, where the batteries provide high energy density for long duration supply, but typically have slower charge and discharge rates. So batteries, the good things about it is that it's got a high energy density, but it's got a typically slower charge and discharge rates. Whereas the supercapacitors offer high power density to deliver and absorb energy quickly. So the charging and discharging is much faster, and it's ideal for handling short bursts of high power demand. So let's just look at these two terms first: energy density and power density. So what it means is that the energy density is related to the amount of energy stored per unit So if we have a battery and a capacitor, energy density is referring to the amount of energy being stored in one unit of this battery or capacitor. Whereas the power density is talking about the amount of energy that can be discharged per source unit over 1 unit of time. So basically is the rate of the energy expense. So for batteries, the rate of the energy expense is slower compared to the capacitors. It can dispense the energy very fast over a short duration of time. So that is the fundamental architecture of the hybrid energy storage systems, where both batteries and supercapacitors are combined into an integrated system where it will supply the electrical power needs of the aircraft. So in a diagrammatic form, the HESS is optimizing the energy management. And how does it do that? It's by balancing the load between the batteries and the supercapacitors during takeoff and landing. So during takeoff and landing, the power consumption, electrical power consumption of the aircraft will increase, and that can be taken care of by the supercapacitors, because the supercapacitors can provide high power needed during the takeoff and landing, and that actually reduces the strain on the battery systems. And then once the aircraft is in flight and it's in the cruising phase, the batteries can supply the steady long-term power needs of the aircraft. And in emergency situations, because it's got a very high energy density, emergency situations, it's got a big reserve, so it can be used. And supercapacitors can deliver power in case of sudden demands or system failures. So we are actually leveraging on the positive side of positive aspects of the batteries and the supercapacitor and putting it together so that we have a very well optimized energy system, supply system in the aircraft. So how does it benefit the aircraft? It will have a very optimized energy system, but it comes at with some challenges like the complexity and cost, because to excuse me, to have two sources of energy and integrating it into one single system is technically challenging, as well as the weight, which is a crucial factor in aviation, as I mentioned earlier on. So because we're going to add a battery and then we're going to add supercapacitors, and then an integrated system may actually result in a bigger, higher weight or more weight to the aircraft. And also the thermal management of batteries and supercapacitors. I mean, these are all energy sources, and when we start to drain power out of these, or when we start to charge it with charging current, it's going to have heat emitted, and that thermal management has also need to be taken care of. So in terms of a block diagram, this is a HESS architecture, high energy storage systems. We have the battery on one side and the supercapacitor on one side. Each one will drive the DC-DC converter to make sure the power that is coming from both the battery and supercapacitors are all conditioned before we feed it to the DC bus, the DC electrical bus. And the DC electrical bus can then be tapped by our electrical load in the aircraft, and all will be supplied by the electrical load. So to the electrical load, it's very transparent on where the energy or power is coming from under various conditions, like during the takeoff, landing, cruising, emergency situations. It will receive optimized power, what it requires, both from the battery and supercapacitor as determined by the HESS architecture. Still on the topic on energy storage systems, technologies. So we have the hydrogen fuel cells. Hydrogen fuel cells are not really new in this area, in battery technologies. Hydrogen fuel cells for manned aircraft is still not mainstream yet, but then it is focused on enhancing the efficiency and reducing emissions and extending the range. So it's got a huge potential, and in fact, it's already gaining traction to revolutionize sustainable aviation with cleaner and longer lasting solutions, energy solutions. So how is it achieving these cleaner and longer lasting energy solutions, especially the cleaner part? We have to look at how hydrogen fuel cells generate electrical power. So it's actually the inverse of the hydrolysis process, where hydrogen and oxygen are supplied to the cathode and anode of the battery, and then the hydrogen diffuses outwards towards the cathode, and then it reacts with the electrolyte. For example, it could be a potassium hydroxide that is sandwiched between the cathode and anode. And then it releases electrons, or basically the current that flows through the load and reaches the anode again. And fuel cells will only produce water and heat. So electrolysis is the process of splitting the hydrogen and oxygen atoms. This is like the reverse, where we have current flowing through and combining the hydrogen and oxygen atoms to produce water and heat. And what we get out of it is we have electrical power generated, but the um, byproduct of it is just water and heat. So no harmful emissions, and therefore it's a cleaner energy power source. The biggest challenge for fuel cell in manned aircraft is ensuring sufficient power density, because we have to carry a lot of hydrogen. So the hydrogen tanks has to be installed and filled in the aircraft, so that the oxygen can mix with it, and then we can have our current. The other thing is to have hydrogen, which is very highly flammable. In the manned aircraft, safety has to become priority, and therefore, in all flight conditions, we need to ensure that the hydrogens do not react and result in any catastrophe. So these are the challenges to hydrogen fuel cells. On January 19, quite recently in 2023, Zero Avia, a US and UK startup, actually flew a Dornier aircraft, Dornier 228, with a fuel cell powertrain. So this is a success story for hydrogen fuel cells, where it replaced one of its two turboprops engines. That means one of the two turboprops engine, one was running on a normal fuel engine, while the other one was powered by a fuel cell, and it took a flight, and it happened successfully for 10 minutes. This is a success story of fuel cell being employed in an aircraft. Of course, it's in a electric hybrid solution. And the principle of the operation is basically the liquid hydrogen being stored on board. So the aircraft had liquid hydrogen stored on board, and it was in lightweight tanks, and it supplied the fuel cell system to generate zero emission electricity. So electricity was generated, but the byproduct was no harmful substances released. So generated electricity was used to power motors. That the motors eventually turn the generators to provide thrust. So if you see this picture, one of the propeller was driven by motor, the other one by a fuel-driven engine, and both worked hand in hand to complete a 10 minutes test flight successfully. So this is a success story of hydrogen fuel cell. Still on the topic on advanced energy storage technology. So one of the things that needs to be up to date is the advanced thermal management. So batteries heat up as the aircraft's motor draw power. So the aircraft batteries in either fully electric or hybrid electric aircraft, the purpose of it is to run the motor, which is eventually going to run the propeller. And because the motors are going to draw significant power from the batteries, there's a risk of thermal runaway in the batteries itself that may lead to fire or explosion. So thermal management technologies has to keep abreast with the technological advancement in the batteries itself. So there are enhanced cooling mechanism or cooling systems that's being developed, focus on improving the longevity and safety of the aircraft. So for example, the Honeywell's Attune, which was formerly known as a micro vapor cycle, is like an air conditioning system, and it actually optimizes cabin cooling and battery temperature. There are also like Airbus innovative cooling technologies that prevent overheating. These are a little these technologies are proprietary of these companies, so there's very little information on how these systems actually operate at a lower level. Nevertheless, these systems are being offered to many of the aircraft manufacturers as part of the advanced thermal management system. So if you were to see here, Honeywell was selected by Lilium, which is a aircraft manufacturer, to provide more sustainable, efficient thermal system for the electric jet that Lilium is developing. And there's a little article here that mentions about the importance of battery cooling in the aviation sector. Okay, so we are like halfway through the presentation, and it's a good time for us to take a little pause here for about 3 to 5 minutes. And then while taking the pause, we can ponder over these little notes here or quotes on sustainability, and we'll come back to this topic again in 3 to 5 minutes.
Oh, well, prepared for this presentation.
Okay, welcome back. Let's move on from where we stopped. Next, we will look at power management and distribution. So innovations in electronics and distribution systems, especially the power electronic distribution system, and they are like optimizing the efficiency of electrical systems. So efficient power converters advanced power management algorithms. They are like integrating renewable energy sources, and it's leading to a much better managed power on the aircraft. So efficient power converters are gaining much traction. If you were to see the traction rate, the global aircraft electrical solid state power control market was valued at US dollar 476.9 million in 2023 and is expected to grow at a compounded annual growth rate of 9.48% through 2029. So that's a 10% increase in the growth rate over just a couple of years. So the technological innovations and demand for the reliable, efficient aircraft electrical systems are driving this growth. So what are these solid state power controller? They are actually the traditional circuit breakers that are being replaced by solid state system. So the traditional circuit breakers in the aircraft, they are mechanical, and it's got a lot of maintenance involved because it's a mechanical system, and it's heavy in weight because it's got a lot of parts inside like springs and all that. So these are being replaced by the solid state power controllers, which actually manage and distribute electrical power in the aircraft. So these are lighter weights because it's solid state, it's using electronic parts, and that is leading to reduced maintenance. And in fact, it will also offer precise and faster control. The response time for, let's say, a circuit to trip will be much faster because it's solid state, no moving parts, and it's going to be happening very fast. And that also improves the safety. So therefore, it's a very highly becoming a very highly sought after power management and distribution component. And if you were to see one of these articles here, there are actually speculations that the end of circuit breaker is coming soon, and as smart power makes its mark in the aviation industry. So under the power management and distribution system, efficient power converters in the form of solid state power controllers, and the development in this particular technology is driving, or rather contributing towards the manned aircraft sustainable electrical and electronic systems. Next, still under the topic on power management and distribution are the advanced power management algorithms. So predictive maintenance algorithms. So these are like software systems where it's doing a predictive maintenance algorithm, such as the ones that are being developed by GE Aviation. They use real-time data to predict and prevent potential engine failures, and that's enhancing the reliability and reducing downtime. So the predictive maintenance algorithms will capture data in real time on operating systems, and then it will predict when a next failure could possibly happen based on this big data. And also that will help to prevent potential failures because we have already predicted it, so we can take action to make sure it does not happen. So the maintenance itself, or rather the coping with a failed system, diminishes. An example will be the electrical load management system, in short it's ELMS, on Boeing 777. Boeing 777, it has been around for quite some time, but this is an example of how these advanced power management algorithms work. So in the Boeing 777, it has algorithms where it will dynamically adjust power distribution based on load monitoring. So the system will dynamically adjust the power. If let's say the electrical loads, many of the electrical loads are being turned on in the aircraft at a certain time, then the amount of power that is being required has to be increased. So the system will dynamically increase the power that's to be distributed by these systems. And then once some of these systems have stopped or not in operation, then the system is intelligent enough to bring down the power consumption or the power distribution so that no energy is being wasted. And at the same time, load shedding under certain situations, like for example, an emergency situation. For example, if there's one of the generators in the aircraft has failed, then we need to conserve energy. The conservation comes in the form of load shedding, where the system will cut the supply of power to non-critical systems. For example, the in-flight entertainment system, which is something that will not have a priority when there's one generator down on the aircraft. So the load shedding will happen where the supply to these non-critical, non-essential systems will be stopped. And then it will have redistribution and predictive load management. That means over the course of a certain flight, the system is smart enough to know that at this point in time, the electrical load demand is going to be increasing. So the power to the entire system needs to be increased. So this real-time based optimization of energy provides for an overall efficiency or overall efficient use of the power system on the aircraft. Energy harvesting system, Boeing has used it. It's like using regenerative braking and other sources. So for example, when the aircraft is braking, that means a lot of energy is being, instead of just wasting it, is being channeled back to the aircraft itself, and then it's used to perhaps charge the batteries and conserve this energy. Then we have reduced fuel consumption, and that will also depend on the battery health monitoring systems, like for example the Honeywell's advanced algorithms that continuously monitor the battery health and performance. So all these are ensuring optimal charging and discharging cycles to extend the battery life. And how does it contribute to a more sustainable aircraft design? When we have extended the battery life, then we are actually reducing the electronic waste. We don't need to like keep replacing batteries, and that will itself be contributing towards a more sustainable aircraft operation. Next, we'll look at the integrated modular avionics. This is an advanced avionics architecture which consolidates multiple aircraft functions into a single modular platform. Example would be like software-defined radios. So we may have traditionally had many radio systems in the aircraft. Now it can all be controlled from a single modular unit. Unlike in traditional avionics systems, where we have a hardware for each function, integrated modular avionics will integrate all these different functions into a single hardware module, and that will actually reduce weight and enhance the flexibility of the avionics system. So this is a little graphics we got from the Thales group. If you can see here, in the 1970s to 80s for avionics systems, we had one box, one function, and typically it's an analog only function. Then in the early 90s, we started to have one box and it performed one function and mainly all digital functions. And then towards the mid 2000s, we had one box that had multiple functions. And by the middle of 2015 onwards, up till now, we have advanced so much that now one module will take up to about 10 functions. So things are becoming more and more integrated in the aircraft avionics systems. And that is a good thing because we will reduce the weight and enhance the flexibility of the avionics system. So for example, the Boeing 787 Common Core system is a centralized system, and unlike the traditional approach of having dedicated electronics for each aircraft function, we have a shared common hardware platform and a core operating system, but a whole host of operational software for various airplane systems. So one module, taking care of multiple functions that were traditionally used, being taken care of multiple boxes in the aircraft. So IMA actually contributes to sustainable manned aircraft operation in several ways. It reduces the number of separate hardware components. Now everything is integrated into one big system. So therefore we have weight reduction, and that will actually lead to lower fuel consumption, which means reduced greenhouse emissions. Next, we have easier upgrades and maintenance, and therefore we will reduce electronic waste. Improve efficiency and reliability. For example, more sustainable flight operations like the Collins Aerospace ProLine Fusion is a smart system where it can optimize flight paths and fuel usage. So the system is intelligent enough to optimize the path, and that can lead to lower fuel usage. These capabilities not only improve the overall performance of the aircraft, but also contribute to a more efficient and environmentally friendly aviation operations. However, it doesn't come with no challenge, full of challenges. One is the complex integration, and it's actually very technically demanding and time consuming to integrate all these various functions that used to be handled by separate hardware into now one integrated seamless system. So the technical complexity is demanding and it's going to be time consuming. And then the certification and compliance, because previously the hardware were individual, now we combine it all into a single module. So the tests to ensure that it's all meeting the stringent regulatory standards for multiple hardware systems now all lies onto this one particular module, and that requires a stringent test process in order to be certified. So the certification process is very daunting. Next, because of the increased connectivity between the systems, it's going to expose itself to cybersecurity risks, and therefore that part of it has also got to be taken care of. We wouldn't want cyber to expose the integrated modular avionics to be exposed to cybersecurity risks. So a lot of IT knowledge has to come in. And finally, with all these challenges, is going to drive up the cost, and the cost significant upfront costs to the airlines and manufacturers who must invest in the new infrastructure, training, maintenance to support these advanced systems. Despite all these challenges, because of the advantages of the integrated modular avionics, it's still being very attractive for consideration for wider adoption in modern aviation. Lastly, we have the lightweight materials. So there are advancements in lightweight materials, components, and manufacturing processes that are applied to the electrical and electronic systems and contributing towards a sustainable manned aircraft operation. So first, we have the graphene-based components. These are components that have good electrical conductivity and strength and are being used in batteries, but not mainstream yet. It's still in its early research phase for aircraft application. Next, we have the carbon nanotubes, which are lightweight, high-strength wiring conductive materials. And because of its lightweight and high strength, is gaining traction and more attention to be used on aircraft. Then we have the carbon fiber reinforced polymers, CFRP in short. These are lightweight electronic enclosures. So used in these enclosures, it has got a high strength to weight ratio, and that makes it very attractive for manned aircraft avionics implementation, such as the A350 and Boeing 787 are using some form of carbon reinforced polymers. Additive manufacturing, in other words, like 3D printing, which is a subset of additive manufacturing, are actually customized complex lightweight components. We can produce it with additive manufacturing, and that will reduce material waste. Then we have the advanced surface treatment. So we can use laser to treat the surface of many of the electronic surfaces or enclosures in the aircraft to allow the coating to be much more to enhance the adhesion of coatings to these laser textured surfaces. So we don't need to put multiple layers to ensure its adhesion. Just with these laser treated surfaces, one of two coatings will ensure its adhesion, and that will lead to less materials being used. And in fact, it will also lead to the reduction in weight. Robotics, automation, and AI. Now AI is prevalent in everywhere, and so it is in the aviation arena. That leads to precision and efficiency in manufacturing processes. So it can lead to consistent quality, reduced material waste. And that along the same vein, AI enhanced design optimization, because AI can actually allow us to have a design optimization, which will lead to reduction in weight as well as reduction in materials. So in conclusion, we have looked at these five areas: more electric aircraft, advanced energy storage technologies, power management, integrated modular avionics, as well as the materials, components, and manufacturing processes, all through the lenses of electrical and electronic systems, and how it's going to be contributing towards a more sustainable aircraft design, particularly in the manned aircraft area. So in conclusion, Developments in the sustainable aircraft electrical electronic systems hold great promise for the future of sustainable aircraft design. There are numerous challenges that need to be overcome. Nevertheless, it will be overcome with a few more years of research, development, testing, certification, and adoption. And the aviation industry, because it's evident that it's continuously innovating, so we can expect advancements and potential implementations in the coming years that will propel the pursuit towards the sustainable aircraft design. So with that, I have come to the end of this presentation. There's a short Q&A time that's allocated to me. If there are no Q&A, then thank you for your attention. We will now await the next presenter to come on, which is my colleague.
Okay, thank you, Mr. Schenker, for the wonderful sharing. So, do you have any more questions for Mr. Schenker? If not, I would invite the next speaker, Dr. Tan Hui Xiang, okay, to share his content on the unmanned aircraft. Okay, Dr. Tan, please. Yes. I will use the keyboard. I think we change the slide.
Okay, good afternoon, everyone. I'm going to talk about developments in sustainable unmanned aircraft electrical and electronic system. So we'll be looking at the overview of some of the recent developments in sensors, electronics, and components. Over the next hour or so, we'll be looking at electric versus fuel-based propulsion, hybrid propulsion, innovations in battery technologies, solar-powered flight, lightweight materials, some efficient components in modern days unmanned aircraft, and we also look at example of UA with many components and how some of these components are making the performance so much better compared to previously. Here we see that we have two types of unmanned aircraft. In fact, two helicopters. Over here on the left will be a electric-based propulsion helicopter, and over on the right you see that based on this smoke, you know that it's a fuel-based. This is a nitro-based helicopter. So which would you say is more sustainable? I would think that the one on the left, the electric one, will be more sustainable because one thing is that the fuel or any type of fossil fuel may one day run out. Whereas if let's say we can power using electric, we can potentially harvest electricity from maybe the sun, and the sun has been there with its nuclear fusion for billions of years. It will still be there. When it's no longer there, we also not be there. So this is like one way I think we should go towards electric-based propulsion. In fact, if you were to see this gas helicopter, even though it's nitro gas powered with an engine, there will still be a need to carry battery to have the electric power to move the control surfaces. The servo needs to turn the hub, and so on. In terms of environmental impact, electric drones or unmanned aircraft produce zero emission during operation, making them more environmentally friendly compared to fuel-powered ones, which emit greenhouse gases and other pollutants. The cost of electricity is also generally lower than that of fuel. I believe you will know that if you were to buy gas, that means gasoline. Gasoline is so-called tax and so on. Whereas compared to electricity, which is consumed by everyone, it is not taxed. Additionally, the electric unmanned aircraft can be recharged using renewable sources, further lowering costs and environmental impact. In terms of regulatory compliance, many regions have strict regulation regarding emissions and noise pollution. In fact, if you were to fly maybe to London, you realize that there will not be any flight landing in London Heathrow from probably 11 p.m. to 6 in the morning. This is due to the strict no-fly or the limit on noise emission over at London Heathrow Airport. Unless, of course, it's a case of emergency, then probably they might still allow an aircraft to land there. So electric drones are more likely to comply with these regulations because it's relatively quieter for electric motor versus so-called gas kind of engine, which would really depend on the maybe silencer or that to lower the sound level. So while fuel-powered drones or unmanned aircraft can offer longer flight times and higher payload capacities, the benefit of electric propulsion actually makes it a sustainable choice. Next, in terms of sustainable power, you see that there are actually efforts by our government or Singapore to make our power more sustainable. Over on the left, you see Channel News Asia says that Singapore grants conditional approval for Sun Cable to import 1.75 gigawatt of electricity from Australia. So over at Australia, they have vast open land or land which are not used. So this can be used to to grow or put the solar panels, and then this can then be transmitted via cables to Singapore. Also, not too long ago, Keppel Energy granted approvals to import 1 gigawatt of electricity from Cambodia to Singapore. So over at Cambodia, there's possibility of solar energy, hydropower, and potentially wind power. In Singapore, we see that we have solar panels probably almost in most parts of the island on HDB blocks, on maybe Bedok Reservoir, Tengah Reservoir, and so on. And 2 days back, during Budget 2025, it was mentioned that authorities will study potential deployment of nuclear power in Singapore. So all this will actually lead to so-called sustainable powering of unmanned aircraft. Next, hybrid propulsion. What comes to your mind when we talk about hybrid propulsion? To me, would be this blue taxi on the left. So this is a Toyota Prius. It is actually a so-called one of the earliest hybrid propulsion, meaning it runs both on gasoline as well as an electric motor. And it is so fuel efficient because it runs on it is designed based on a different type of engine. This Prius is a so-called Atkinson cycle kind of gasoline engine. So compared to the normal engine we have, which is the Otto cycle engine, this one is much more efficient. But the problem is, okay, the trade-off is that it has lower starting torque. So at low speed, it will not have the so-called suitable amount of torque to fulfill the so-called driving performance. Hence, the electric motor comes in and then it helps because it provides the high starting torque, which is typical of electric propulsion. Now, it's very obvious, right? You see all the EVs, be it Tesla, BYD, whatever, you see them accelerate off the red light. It's like almost instantaneous. Also for so-called hybrid engines for aircraft, right? We see this so-called unit here. It combines a combustion engine unit as well as generator unit. And if you see the 3 tuning fork over here, this is the one by Yamaha. So Yamaha does engines, motorbikes, musical instruments, all that. So you recognize by the 3 tuning fork. So hybrid powering of unmanned aircraft combines, as mentioned, the ICE, internal combustion engine, with electric propulsion system to optimize performance and efficiency. These hybrid systems are particularly beneficial for applications requiring long flight, heavy payload, or operations in remote areas where charging infrastructures may be limited. So sometimes certain places, they really do not have that amount of electric power. So even in some countries, the people there may tell you, if I on the rice cooker, I can't on another device. It will trip the power supply. So in that sense, then the fuel comes in useful. Here are some key aspects of unmanned aircraft systems, like hybrid unmanned aircraft systems. It allows for increased range and endurance. Hybrid system can extend the range and flight time of unmanned aircraft by using the ICE for cruising and the electric motor for takeoff, landing, and other high-power maneuvers. By combining the strength of both power sources, hybrid system can achieve better fuel efficiency. The ICE can run at its most efficient point, while the electric motor can provide additional power when needed. You might even see this in some cars on the road, like for example, you see the Nissan e-Power. Nissan e-Power actually runs a so-called engine which is purely used to generate electricity. In that sense, because it's not affected by road conditions, the engine can run at whatever most optimum speed to be a electrical generator. Then the car is propelled by electric motors on the wheels. Next, reduce emission. Hybrid system can reduce overall emission compared to purely fuel powered unmanned aircraft. The electric motor can handle parts of the flight where emissions are most critical, such as takeoff and landing. It is also very versatile because it can be used in a variety of applications, from long endurance surveillance mission to cargo delivery. The flexibility of switching between both power sources allows for optimized performance and so-called to meet the mission requirements. Also, when there are two power sources, it increases the reliability of the unmanned aircraft. If one system fails, the others can take over, probably providing limited lift or what to allow for a safe landing. Hence, it enhances safety. Modern hybrid UAs are also equipped with sophisticated control systems that manage the power distribution between the internal combustion engine and the electric motor, hence ensuring optimal performance and efficiency. Next, I will cover battery technology. Um, I would say that battery is such a so-called important commodity or product. Can you imagine? And in fact, because of that, right, Nobel Prize 2019, as seen here, was awarded to John B. Good Enough and M. Stanley Whittingham and Akira Yoshino for their contributions to the development of lithium-ion battery. Can you imagine, without this lithium-ion battery, if we were to have any electronic devices like your phone, you might have to buy a few sets of, say, AA size battery every day. And this is going to cost like $10, $20. And come 1 month, this amount spent on batteries might come to a few hundreds. And this would make actually a lot of electrical devices not possible. So with this invention of this high capacity battery, it actually allows for many possibilities. Over here, see innovations in battery technology such as lithium sulfur and solid state batteries are enhancing the energy storage capabilities of UAs. These advancements allow for longer flight times, greater payload capacities while maintaining sustainability. Imagine if we have a good electrical system, so-called electric powered unmanned aircraft, but if it allows it to only fly like maybe 10, 15 minutes, then it's not going to be adopted because typical missions might require a operating flight time of maybe half hour, 45 minutes, or 1 hour. Hence, the battery and its ability to supply enough electrical power is essential to allow adoption of electrical powered unmanned aircraft. Let's look at this first battery, a very classic one. Anyone seen this before? This would typically appear in maybe two places. One will be the alarm boxes. So alarm or emergency backup lights. This is a lead acid battery, 12 volt, 9 ampere hour. Lead acid batteries have relatively low energy density compared to other types of batteries. Their typical energy density ranges from 30 to 50 watt hour per kg. Due to their low energy density, they are widely used only in some applications like for your car, where you start up your engines, and as backup power supplies, maybe your UPS, uninterrupted power supplies, and so on. So over here, a simple calculation, 12 volt, 9 ampere hour, and the weight is 2.52 kg. If I were to just do some multiplication, it gives energy density of 42.85 watt hour per kg. So if the energy density is so low, it makes it practically impossible to use it for flying because the dead weight itself, the weight of this item is already so heavy. And if you compare this to fuel, a fuel aircraft, as it flies, the fuel is being consumed, the weight actually decreases. Next, let's compare lead acid battery. Next, nickel cadmium battery. I think now it's no longer allowed in EU. Before that, these are used in maybe powered tools on aircraft and so on. Slightly higher energy density. Nickel metal hydride rechargeable battery. You will still see this on your maybe so-called remote controls. So typically AA or AAA battery still uses nickel metal hydride, 1.2 volts nominal voltage. So slightly higher energy density. Next, this one is so-called the one which helped the three inventors get the Nobel Prize award. Lithium-ion battery. If you have seen this Nokia battery, probably your IC number starts with S. You have not seen, maybe it starts with T. So it practically now we don't see this kind of so-called removable lithium polymer battery. We see batteries which are embedded, something which looks like this on the bottom right. And then this on the so-called this green one, it might look not very impressive, but do you know that in fact this is the one which is used to power the first generation Tesla? They have all this arranged in blocks and connected in series and parallel, about close to 7,000 pieces. And with cooling, it can run your Tesla Roadster and some of the older models Tesla. UA typically uses lithium polymer battery. Over here we have got a 4 cell, so 14.8 volts, 6 ampere hour, and discharge capacity of 75 times of capacity, meaning the maximum current it can supply is 450 ampere. So in fact, if you take a 3 cell 12 volt one, it will easily start your car with no problem. Okay, in fact, one of the problem with batteries is that if the weather is too cold, it is not going to work properly. Like you see in some winter countries, the Teslas charge for a very long time, but it doesn't work. So over here, what we have is a DJI Mavic 2 Enterprise battery. This one has a self-heating function, and it allows operations in unmanned aircraft in cold temperature to work as low as in minus 10 degrees Celsius. Next, you might have heard of solid state battery. This type of batteries uses so-called solid state electrolyte instead of liquid or gel type electrolytes. The electrolytes are typically ceramic, gas, solid polymer, or made up of sulfides. Compared to lithium-ion batteries, they are more efficient, pack more power, given a same the compared to a battery of the same size. As a result, EV batteries can become more compact, charge faster, weigh less, and so on. You will wonder, why am I talking about EV batteries? Because typically, if batteries in one type of application can improve, so can it be adopted later on. No doubt we cannot so-called detect what is being used in unmanned aircraft, but with an overall market having better battery technologies, it will later be implemented and allows for uh, so-called longer flight time or a battery which can last for maybe many years. So we don't have to worry about all the used batteries after their useful charge cycles being discarded and so on. That will in fact lead to more pollution. Next, sodium ion batteries. These are similar to lithium ion batteries but uses salt water as an electrolyte. Although it has lower energy density, but so-called is much more affordable and very safe due to the low risk of fire. It also performs better at low temperature compared to lithium-ion batteries, and sodium being more abundant and cheaper than lithium will make these batteries an attractive option for large-scale energy storage. So companies like CATL are leading the development of sodium-ion batteries. Next, lithium-sulfur battery. This new battery technology uses sulfur as the battery's cathode, which is more sustainable than nickel and cobalt typically found in the anode with lithium metal. It is more efficient than lithium-ion batteries, which could increase the range and storage capacity. Additionally, sulfur is more affordable and abundant, which could mean lower costs. And since the manufacturing process for this battery is like the one used for lithium-ion batteries, the same facilities could be used for production. Advancements in lithium-sulfur batteries have also resulted in ultra-fast charging and made them more useful for raising the storage capacity of renewable energy technologies. One of the major drawbacks of this new battery technology is corrosion, though these new designs are in the works. Though there are new designs in the work to curb this. Another advantage is that these batteries don't last as long as lithium-ion batteries. So we shall see in time to come whether this becomes mainstream. Many types of cathodes. So we have NCA battery, NCM, and LFP. You might have heard of LFP, lithium iron phosphate. These are used in the blade batteries over here for the BYD vehicles. And these batteries are in fact being used in the newer Tesla models as well. So you see, typically previously they used the 18650 battery. So as mentioned previously, the small round battery, maybe 7,000 of them, used to power the Tesla Model S, Model X. Then the 21700, the larger one, which has a higher density as well. We see here this news article, Tech in Asia, says that Cherry to mass produce solid state batteries in 2027. And just now, we saw that maybe the lithium ion battery capacity is probably 200 over watt hour per kg. But over here, this battery can achieve energy density of 400 watt hour per kg. So the target is to achieve 600 watt hour by 2025. Next, we take a brief look. So you have heard earlier from Mr. Schenker that there are solar powered flight and so on. So we will also look briefly at solar power flight because unmanned aircraft being smaller and lighter, I think it's even more possible if it can be used to partially power large commercial jet, right? So solar power flight are still the experimental phase and specialized use stages, but they hold great promise for the future of sustainable aviation. Imagine something which doesn't cause any pollution. We see two examples of solar power flight. One will be Solar Impulse 2. This aircraft you see with long wing, narrow body. So I think you need specialized skills to fly it. May not be that easy. But it completed the first solar power flight around the world in 2016. And this aircraft used solar panels to generate electricity, allowing it to fly without any fuel. So you see the big surface area of the wings probably is all filled with solar panels. Next, Airbus has this Zephyr, a high-altitude pseudo-satellite that can stay afloat for months at a time using only solar power. This unmanned aircraft is actually designed for long endurance mission and can provide high-quality imagery and communication services. Moving on, we shall look at lightweight materials. So you would have heard of some of these materials like the carbon reinforced polymers, known for its exceptional strength and weight ratio. So we will not go into much detail. So in short, it provides excellent stiffness and durability. This makes it ideal for both racing and industrial unmanned aircraft. So why so? Probably I'll talk about this after this. Then of course there are glass fiber reinforced polymers, aluminum alloys used for motor mounts and frames, and also various plastics such as ABS, nylon, PC. polycarbonate for different parts of the unmanned aircraft. So ABS is known for its impact resistance, nylon wear resistance, and polycarbonate for its toughness and transparency. Also, magnesium alloy. These are lightweight and strong, make them suitable for components that need to withstand high stress while keeping the overall weight low. So Kevlar is also being used. So this is something like those materials used for helmet, very strong and lightweight. The advantage of using carbon fiber frame for drones is as follows: it's lightweight yet strong. It has excellent strength to weight ratio. So with this lightweight, right, we are actually improving the performance of unmanned aircraft. Typically, when someone talks about performance, it means how long it can fly and how much it can carry. So if let's say we can reduce the weight, then it's going to improve flight performance and efficiency. Also, carbon fiber is highly resistant to wear and tear, and even under prolonged stress, which is ideal for drones that undergo repetitive cycle. So unlike metals, the carbon fiber does not corrode and enhances the UA's lifespan and reliability in various environments. It is also stiff. I need to just let you know that stiffness of carbon fiber is very important because in order for an unmanned aircraft to fly well, the brain or the sensors of it actually needs to sense whether the aircraft is maybe tilted or horizontal or flying level. So because of that, right, if there are anything which is not rigid, that means it vibrates, it's going to affect flight performance. So it may wobble, it may perform badly, or it may even crash. Next, thermal stability. Carbon fiber maintains its strength at high temperature, making it suitable for drones operating in extreme conditions. By now, you should have seen, like for example, some drones are being used in maybe Mount Everest to deliver something from the base camp up. So it's even capable of like generating sufficient lift at such high altitude. So very amazing, lots of applications. Next, improve flight time and being maneuverable. So the lightweight reduces the energy required for flight, leading to longer flight time and more maneuverable. We look at some of these components. So, for example, the motor which is being used on unmanned aircraft are typically brushless motor. They offer higher efficiency compared to brush motor. Typically for brushless motor, it's about 80 to 90% efficient compared to 70 to 80% efficiency for brush motor. This is due to reduced energy loss due from friction or heat. And brushless motors also require much less maintenance since they don't have brush that wear out over time. This leads to longer lifespan and more consistent performance. Next, brushless motor operate more quietly and also with less vibration compared to brush motors, which can be important for application where noise is a concern. While brushless motor is generally more expensive upfront, their longer lifespan and lower maintenance costs can make them more cost effective in the long run. After all, if I were to ask you who has experienced so-called maybe DJI unmanned aircraft failing, it is not so likely because they run on brushless motor as well. So let me just show you on the left, we have this Tamiya car motor, two terminals. So one will be positive, connect to positive, and the other connect to negative. And once you connect to the battery of the correct voltage, it starts to spin. So this is the brush motor. Inside there is brush, even though you can't see it. Compared to this on the right, you see there are three wires leading to the motors. When you just choose any and you connect a battery to it, what happens? Nothing happens. Because in fact it's similar to an AC motor or a brushless motor. You connect a battery, it will not move. So later we'll see how to make it move if we have time. I illustrate something very simple. You see the SMRT train here. This is the Kawasaki C151 train, both before and after refurbishment. So over on the right, on our right, so the left side of the track, there is a third rail which supplies maybe 700 volts or how many kilovolts, I'm not sure, 700 volts or 700 kilovolts. You can take a look when you go to MRT track. So this is DC. So does it mean the train runs on DC motors? No. As seen here, it runs on a permanent magnetic synchronous motor. Why? Because it's an AC motor. There is no brush. It's brushless. It is going to last a long time. It wouldn't fail. So to make it move, there must be an inverter system which varies the frequency to give you a variable frequency AC supply to move the motor and propel the train forward or backward. In fact, it's so common. You see these two power tools. This is the Makita power drill. You will see this drill when you order IKEA furniture and the fitters come and fit your furniture. It will be a Makita, a Bosch, and some other brands, the typically more reliable brands. So this is a new one. You see is brushless. You see the word brushless here? It runs on brushless motor because it is the way to go. It is efficient, it's durable, and it will last a long time. It will not fail you. So the older ones, you will see that on the cover, on the back here, there is some screws for you to take out the cover, and you can replace the brushes which looks like this. So over here, this brown portion is the carbon brushes, which will wear out over time. When it fails or finishes, you hear some funny sound, you smell something, but the motor does not turn. So this point here is in contact with the commutator. Don't worry, if you have not done electrical kind of courses, you will not understand it's normal. So just know that it brushes against something and it will cause friction and heat. And as a result in some loss in efficiency. So brushless motor are used on most unmanned aircraft nowadays. They last longer. They must power through a ESC, electronic speed controller. We will not go into detail what this is, but in short, it is something which converts DC to AC pulses or currents, and then it turns a motor. So the motor looks typically like this: a stator which does not move and a rotor which turns. So when there are some electrical fields, it interacts with the magnets on the bell and it turns the motors. Next, I will talk about the flight controller, which is in short known as the so-called is called the brain of the multi-rotor aircraft. Why do we need this brain? Because for a multi-rotor, for example, a so-called quadcopter, that means four rotors, four motors. So in order to fly right, the four must spin at a certain speed, which will result in the so-called quadcopter frame staying level. It cannot spin in some funny manner, then it will maybe spin out of control and so on. So it's a coordinated kind of like motor spin to allow it to go up, down, to roll left, roll right, pitch forward, backward, and so on. So it contains so many sensors such as gyroscopes. Gyroscope sensors like your whether something is turning left, right, and so on. Then accelerometers to know whether you are level, you are maybe tilted left, right, and so on. So it's actually three-dimensional so-called accelerometers to measure whether so-called there's gravitational pull in each direction. Then from there you can compute to know whether you are level, tilted, and so on. So magnetometer, which allows so-called the aircraft or the software to know the magnetic heading, is a magnetic electric compass, so as to say. So this allows the aircraft attitude, meaning the roll pitch to be determined. So some flight controller also has a barometer. So it allows the flight controller to sense the air pressure to know its altitude. How heavy would you expect this component to be? I can safely tell you that for aircraft, the spinning gyroscope maybe weighs a few 100 grams or a few kilograms. But if you see this tightly integrated SP Racing F3, so SP Racing F3 is not related to SP, it's just a model of flight controller known as SP racing F3. F3 because it runs the F303 STM 32 microcontroller. Then there are some accelerometers, some magnetometer, and some barometer ICs on board. And this whole thing, which is small, 36 by 36 mm, weighs only 6 grams. So these efficient components actually allows the racing drone to fly fast and be efficient. So over here is a F405 Mark II beta flight controller. F405 meaning again the STM32 controller is the F405 series microcontroller. So below would be the power distribution board stacked together. So later we also take a look at this power distribution board to see why it is so light and helps in efficiency. Of course, there are some other flight controller. So this will be known as autopilot system, as they can be configured to fly maybe a certain waypoint to do some missions autonomously. It mainly uses the GPS information to do autonomous flight when outdoors. So over here, this is a DJI A3 flight controller, a very reliable one, typically used on large unmanned aircraft. And even though this is a so-called more established with aluminum casing and GPS module, it weighs only 186 grams. Next, the Pixhawk here weighs only 15.8 grams. If we were to compare to this, the aircraft IMU, the initial measurement unit, it weighs 4.2 kg. If I were to fit this onto the unmanned aircraft, it simply would not fly, most of them. Next on the efficient component list, we have this power distribution board. It helps to reduce the weight of a UA in several ways because instead of like having many wires to split the power, so if you got one battery but got 4 motors, you have to split this into 4 separate so-called connections. Then you need maybe 8 wires and so on. So all this can be achieved by simply soldering this onto a small lightweight PCB board, which probably costs weighs 6 grams. So it's designed to be compact and fit within the drone's frame efficiently. It minimizes the amount of wiring needed and reduces weight because there's really not much materials, and it improves airflow. By putting components close to their respective connectors and so on, the power distribution board reduces the so-called length of wiring needed. This not only saves weight but enhances the UA overall balance and stability. We do not want to have any wire which is loose, shaking, vibrating, and so on, as we mentioned previously. So this efficient PDB minimizes power loss and ensures that all components receive stable and adequate power. This can lead to the use of smaller, lighter batteries, further reducing the UA's weight. If you were to look at this power distribution board, in fact, it has other things. It has a 5-volt supply and also a 12-volt supply. So 12-volt may be to power the onboard video system. 5-volt is to power the other electronics. Next, battery eliminator circuit. What are BEC? This typically is just an electrical converter, converts the battery voltage to a voltage that can power the UA's electronics, which is typically 5 volts. So we have a large battery or a medium battery, which can be 12 volts, 16 volts, 40 volts, and so on. So your input, output comes 5 volts. This means that you no longer need to carry a small battery just to power the receiver or some other electronics. It can step down efficiently. So what are the various types? So, the older types will be something like this. In your electronics class, you see a 7805 linear voltage regulator. This actually steps down the voltage from high voltage to low by so-called losing the voltage using heat. So it results in lots of power loss and so on. But then when we see these newer ones, we have a switching BEC. So this is, for example, an LM7805. No, this is a LM2596 IC. So it just switches on and off. And this results in a more efficient power conversion and minimal heat loss. So what you can, if in fact you see the so-called power adapter from 10 years back versus now, you realize that previously or 20 years back, it was like a big chunk, very heavy. You open up, inside is a electrical transformer, but nowadays it's so light because it's just a switching power supply capable of like a class 5 or 6 efficiency. So we have this BEC, which is designed to handle higher current, voltage, and provide stable power to various UA components. In fact, some of these BECs has integrated are integrated in the ESC. So over here, you see these three wires, the black and the red. So the red is in fact the 5-volt BEC output, which can be used to power the flight controller. Okay, I think we have come to so-called the second part, which is to talk a bit more about example of a unmanned aircraft. So over here, this is the DJI unmanned aircraft, a DJI Phantom 4. I would just like to maybe discuss with you to show you that this unmanned aircraft can fit so many sensors, achieve so many amazing things, but it weighs only like 1/kg and can do so many amazing things. If I were to ask you what are some of the sensors built in, can you think of some sensors? The hint, this UA is capable of position hold, can fly waypoint, can maintain altitude, and can transmit video to the controller. So it may sound simple, but in fact, it is something which is so difficult. And this platform, small, lightweight, can do all these things. Let's review the answer. Okay, first, GPS module. So, in fact, not seen is that on somewhere on the top surface there's a GPS module, or let me call it just a GNSS, Global Navigation Satellite System module. It can receive GPS signal, Beidou signal, and maybe the Galileo and so on. So various types of satellite signals. So this is in fact so useful because once you have this thing, it can actually sense that your unmanned aircraft is drifting left, right, and from there it can help to compensate back. So imagine the pilot is not giving any inputs, so that means it should stay stationary. But then the computer on board senses that it's drifting left or right, hence it will know that it's drifting and it will compensate to maintain at that particular latitude and longitude position. Next, magnetometer. What is it used for? Why do you need to measure the heading information? So for example, I'm now here at Singapore Polytechnic. In order for me to fly autonomously to, for example, Clementi Mall, the computer on board need to know where am I. First, it knows that I'm at this latitude and longitude. It needs to know which direction to fly to. So by doing a lat-long subtraction, it can then compute the heading to fly towards. So this magnetometer on board, in fact, tells the computer which way to fly to in order to reach Clementi Mall, which is the destination. Of course, we have mentioned brushless DC motors. Then with brushless DC motor comes the propellers. There are some particular direction of spinning. So for example, this, if you turn this around, this is the front left propeller. It must turn clockwise because you look at the pitch of the propeller. The key thing to understand is that the motor must push air downwards because the unmanned aircraft wants to fly upwards. So if you feed it in the wrong direction, you can tell. So, but the DJI is so well designed that there's no way to feed the propellers wrongly. So don't worry. Next, electronic speed controller, which is being used to so-called give the signal to spin the motors. Then, of course, your flight controller, the autopilot, the brain, which balances the unmanned aircraft, spin each motor at a certain speed to have coordinated flight to achieve stable flight. Of course, video transmitter, because there is a camera on board. In fact, DJI is designed to be a flying camera, so it must transmit the video to the ground so-called station or the controller or someone with a video receiver. Next, RC receiver, so it takes in the inputs from the pilot to go left, right, pan the camera to maybe your left, right, and so on. A barometer, this is important because any minute change in the air pressure would indicate to the onboard computer that the aircraft is going upwards or downwards. So similarly, without any input from pilot, it must maintain altitude. It should not go up or down, and hence the onboard computer compensates accordingly. Camera gimbal allows you to have a very stabilized camera. So I need not say much. The influencer, the live streamer, they have a gimbal camera, so their video is stabilized and beautiful. Of course, camera to capture videos or images. Stereo camera. This is something which you might not notice, but in fact, if you look in front, there are two small black dots. These are in fact video cameras which allows the aircraft to stay at a stable position. So if indoor, if I will see, or maybe there's a pillar in front. So without any pilot input, if pilot never give any input on the control stick, and it senses that the so-called the pillar or the pole is moving left, right, it knows that it's drifting, and then it would actually compensate to stay in that position. So that's the so-called vision positioning hole. Of course, below also there are two black dots. So this one allows it to look down. As long as there are some distinct feature, it would not drift. So one way to so-called test your piloting skill, of course, would be to either off the lights. So for optical systems, when there are no lights, it's not going to work. Or you can take the bottom so-called sensors. They will drift left, right. You will not have any position hold capabilities. Over here, beside the bottom sensors, you see two ultrasonic sensors. It helps because when it's nearing the ground, it can sense how far it is from the ground, and it's used mainly for landing. So we have seen how amazing these systems are. So lastly, I would just like to take 5 minutes of time to watch 5 minute short segment. So I wonder if you have maybe watched some video on Amazon Prime. You have watched Clarkson Farm, which features Jeremy Clarkson as well as Caleb Cooper. You realize that when they want to so-called plant or drill the seeds onto the ground, right? They actually have to leave some space for so-called spraying the crops. So they have this tram line which they need to follow so that when it comes to the time where they need to travel through the field, they will not be crushing on the crops. But with advancement in aircraft technology, you can see over here this DJI Agra's T50 allows the spraying to be fully automated, well planned. It allows the amount to be sprayed to be a certain spray rate, and is even, and there's no need to maybe leave tram lines or leave a space on the field for the tractor, for Jeremy's and his Lamborghini tractor to pass through. So let's take a look and see how amazing this system is.
Have our maps. Our maps download, our Google Maps satellite imagery download from the internet while we have Wi-Fi on the remote. We map this field that you see here, and when we get to the field here, actually in the field, we don't have to have Wi-Fi, and we still have satellite imagery. We still have all of our maps. We could have 20 different maps across here. We could just click on the ones we wanted to fly, hit use. We can set our rate, our speed, our height, and our route spacing all right here, or you can just select the template like we've done here, and that fills all that in for you. It's literally it. That's all you have to do. Hit start, and the drone's ready to go. T-50 inherits the legendary, reliable design of the Agris T-40. See, the Agris T-40 sprayed millions of acres in 2023 across thousands of farms. And we had extremely few problems with the powertrain, with the ESCs, with the motors, with the spray systems, with the software. The T-40 is a phenomenal drone and still is a phenomenal drone. So our thought was, well, if it's not broke, why fix it? Why improve a T-40? Why improve the best spraying drone on the market whenever it's already so good? The great thing about the T-50, it's almost exactly like the T-40. Same props, same motors. The frame is almost identical. And the spray system and radar system is even better. Terrain following with drones is incredibly important. You see out here, we've got a flat field. We can literally turn all of our radars off, no obstacles, no terrain challenges, very, very simple operation out here. But these drones thrive in the hills. That's where you have your highest ROI. How do you get an airplane? How do you get a helicopter in the hills? How do you get an airplane? How do you get a helicopter in small fields surrounded by trees? You can't, but a drone can. If you have good terrain following, if you have good obstacle avoidance. And the T-50 brings those to the table. So as you can see here on the screen, we can monitor progress of the drone. We've got the drone's location in red is the triangle, so I already made it down. This is a half-mile long field here. So made it down 2,600 feet, turned around and spraying back. And you can see right here in the middle of the field, it's actually going to be able to spray all the way back to us, then make another half pass back. We're probably going to go ahead and bring it home whenever it makes it back to us to shorten our deadhead time. Up here at the top, you can see we can view our live volume. So we have about 4.9 gallons left. That's volume by weight. T-50 has scales on the tank, and those scales measure the weight, converts that into volume, and gives us a live readout, and that's how we get our empty tank location. We can monitor our battery life. You can see we still have 71% battery. The drone's almost all the way back to us right now. 28 satellites on this drone. You can see it here at the top. Now, most of you guys, if you've ran ag equipment, you've probably seen that you've only got 12, 13, 14 satellites in a lot of fields. We've never had fewer than 26 satellites on the Agris T-40 in any field we've ever operated in, and I expect the same thing out of the Agris T-50. Our altitude, speed, distance, and radar is all on the screen. We can monitor everything right here. And of course, our FPV camera, we can watch it come back home and move the camera up and down as well. All right, I'm going to go ahead and hit that return home button. Bring it back home. It's going to stop spraying automatically and return back home to us and come down to the trailer automatically. There you can see this is new on the T-50. Because of the incredible radar, you can actually spin on the way home and reduce some time, face the same direction as it faces whenever it takes off. That way it aligns the fill port on the same side. Just like that, one tank done. I'll grab a fresh battery because we are at 61%, but we kind of like to swap our battery every time. That way we increase the redundancy, just in case there's a problem out in the field. We use our fill-through cap on the T-50. This is not standard. This is an upgrade from Agris spray drones. Works really well with our filling system.
So with this, we have come to the end of my presentation. So we have seen that drones nowadays really can help you do lots of things. And I feel that electrical power is the way to go, or the electric propulsion, because we have all this renewable energy coming from various sources. And in time to come with improvement in battery technologies, one battery will one day last many years, and we might so-called not need to purchase another battery for the lifespan of the aircraft. So I leave the room now for Q&A.
Okay, thank you, Dr. Tan. Okay, so we hope you enjoyed the 2-hour journey of infotainment that the two pilots has actually shared with you during their sharing. Okay, so okay, I don't see any questions. So now we've come to the end of the second sessions of the webinar series. Okay, so we have one more last session of the webinar series, which is next week. So hope to see everyone again. So goodbye.